Section 4.3, Partial Derivatives. To begin, let's talk about derivatives of a function of two variables. When studying derivatives of functions of one variable, we found that one interpretation of the derivative is an instantaneous rate of change of y as a function of x. Leibniz notation for the derivative is dy dx, which implies that y is a dependent variable and x is independent variable. For a function z equals f of xy of two variables, x and y are the independent variables, and z is a dependent variable. Let's begin with the definition of a partial derivative. Let f of xy be the function of two variables. Then the partial derivative of f with respect to x, written as df dx, or f sub x, is defined as df dx is equal to the limit as h is approaching 0 of f of x plus h comma y minus f of xy divided by h. The partial derivative of f with respect to y, written as df dy or f sub y, is defined as df dy is equal to the limit as k is approaching 0 of f of x comma y plus k minus f of x comma y over k. So I know it looks different, but again, like I tell my calculus courses, I've told them, think of this as your quotient rule, right? Here, notice that we're replacing our x with x plus h. And if we're taking the derivative, the partial derivative with respect to y, then we replace a y with x plus k. And then from there, rely with your definition, your limit definition from calculus and your definition from a quotient rule that you learned back in college algebra or pre-calculus. Moving forward, this definition shows two differences already. First, notation changes in the sense that we still use a version of Leibniz notation, but the d in the original notation is replaced with the symbol, and this is a rounded d. It's usually called the partial. So df dx is spoken as the partial of f with respect to x. Use a function of the partial derivative. Use a definition of the partial derivative as a limit to calculate the partial derivative of f with respect to x and the partial derivative of f with respect to y for the function. Okay, so I'll use definition. So our definition above says that if we're trying to calculate df dx, then I'm going to replace every x with an x plus h. So we have to replace an x there, and there. Everything else stays the same. So that we have x plus h squared minus 3 times x plus h times y plus 2y squared minus 4x plus h plus 5y minus 12. Okay, let's clean this up. So if we square that binomial, we're left with x squared plus 2xh plus h squared. We're multiplying in a negative 3y, so we're left with negative 3xy, negative 3hy, plus 2y squared, minus, distribute that negative 4, negative 4x minus 4h, plus 5y minus 12. Alrighty, well, that is our first part of our definition. So we've managed to complete this first part right here. Now we want to subtract, find the difference from that of our function f of x comma y. So let's write our definition. The limit as h is approaching 0 of, it'll be lengthy. So we first have our first part, the x plus h. So that we have x squared plus 2xh plus h squared minus 3y minus 3hy plus 2y squared minus 4x minus 4h plus 5y minus 12. And then I'm going to subtract my original function. So that causes a sign change for each term, so that we have minus x squared plus 3xy minus 2y squared plus 4x minus 5y plus 12. Okay, so things should add up to be 0. Oh, I forgot, all over h. So let's see what adds up to be 0. We have x squared minus x squared, that's 0. We have 12 minus 12, that's 0. We have 4x minus 4x, and 2y minus 2y. And I think that's about it. So what are we left with? We're left with the limit as h is approaching 0 of 2xh plus h squared minus 3xy. Oh, my xy is also added to be 0. So xy is gone. Minus 3hy minus 4h. My 5y's are gone too. And I believe that's it. All over h. Okay, well, let's factor in h. If we factor out an h, we're left with the limit as h is approaching 0 of 2x plus h minus, oh, my xy's are gone, right? So that one shouldn't be there. Minus 3hy, so it's just a y, minus 4. Okay, well, we go ahead and we divide to make one worth for that h. So we're left with the limit as h is approaching 0 of 2x plus h minus 3y minus 4. Okay, we substitute in the h, so we're left with 2x plus 0 minus 3y minus 4. Our answer is 2x minus 3y minus 4. So we use that definition above. Now, for the sake of not making this video too lengthy, I'm going to ask that you go ahead and you try to find that partial derivative with respect to y. So you go ahead and calculate df comma dy. And your answer should be negative 3x plus 4y plus 5. Okay, moving forward. The idea to keep in mind when calculating partial derivatives is to treat all independent variables other than the variable with respect to which we are differentiating as constants. Okay, so how do you treat constants? Maybe thinking about that separately is helpful. So let's say we have a function, and let's say this function is 1. What would be the derivative of that? Well, the derivative of any constant would just be 0. So we hold that true as we work with partial derivatives. So if we're taking the derivative of something other than the variable we're working with, then it would work as a constant, be treated as a constant. We'll see this in this next example. Calculate df dx and df dy for the following functions by holding the opposite variable constant, then differentiating. So let's start off with df, or should I be proper, the partial derivative of f in terms of x for this function given. F of xy equals x squared minus 3xy plus 2y minus 4x plus 5y. Okay, so we want to take the derivative of this function. So d dx, and let's write down our function. X squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. Okay, so let's work this out. We only want to take the derivative of our x's. Anything else will be treated as a constant. So for my first term, x squared, the derivative of x squared is 2x minus the derivative of x is just 1. So we have 3y. Y, 2y squared, well, that's technically a constant. We know y is a variable, but we're differentiating in terms of x only, not y. So we treat it as a constant. The derivative of negative 4x, that's just 4. 5y, constant, does 0. 12, constant, does 0. So what are we left with? 2x minus 3y minus 4. We have found the derivative of our function f in terms of x. All right, what about in terms of y? Partial derivative of function f in terms of y. So we want to calculate the derivative for the y only. Anything else than the y would be a constant. So we have x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. Okay, so for my first term, well, let me just take a step back. Let's go ahead and point out where our y's are. Those are our only variables. The rest we treat as constants, as numbers. So first I have x squared. The derivative of x squared, well, we treat it as a number. So think of it as like as 2 or 1. Our derivative would be 0 minus the derivative of y is 1. So we have negative 3x. The derivative of that 2y squared would be 4y. The derivative of negative 4x, well, x is a constant. The derivative of 5y is 5, and the derivative of 12 is 0. So that we're left with negative 3x plus 4y plus 5. We have calculated the partial derivative of function f in terms of x and the partial derivative of your function f in terms of y. So, as you notice, this was part A. Let's go ahead and do a part B. So here's your function B. F of x comma y is equal to sine of x squared y minus 2x plus 4. So remember, when you have like two arguments within each other, you have to practice chain rule. So you have to take the derivative of your sine and then remember to take the derivative of your argument. Okie dokie, so let's go ahead and find the partial derivative. Let's start with x. So let's find df dx. So the derivative of a function in terms of x is, well, we're working with sine of x squared y minus 2x plus 4. That's what we're taking the derivative of. And just to highlight what we're working with, our x's are our variables. Okay, let's work this out. The derivative of sine is cosine. Cosine x squared y minus 2x plus 4. And then I have to take derivative of the inside. Only x is our variable. So we have 2xy. That gives me 2x. We're working with x squared y. The derivative of x squared y is 2x, and that y stays. Then we have 2x. The derivative of 2x is just 2, plus 4, plus 0. If we clean it up, we get 2xy minus 2 times cosine of x squared y minus 2x plus 4. All right, let's go ahead and find the partial derivative in terms of y. So df dy. According to our function is sine of x squared y minus 2x plus 4. Okay, So recall chain rule, we have to take the derivative of sine, which is cosine. We keep the argument x squared y minus 2x plus 4, and then we take derivative of the inside. But recall, we're only taking the derivative of our y arguments, and we only have a y once. So our derivative of our argument of sine is, derivative of y is just 1. So we have x squared. There's no y, so it's a constant. There's no y, so it's a constant. The rest are zeros. So our answer would be x squared cosine of x squared y minus 2x plus 4. Not so bad, right? I find it's really helpful to point out, just put an arrow on the variable you're working with, the argument you're working with, so that you don't make the mistake of treating another letter as a variable when it's really a constant. Okay, so how can we interpret these partial derivatives? What does all this mean? Well, you do have some knowledge of derivatives from your experience of Calc 1, but how does these partial derivatives relate to this multivariable course? So, reading from our notes, recall that the graph of a function in two variables in surface R3. If we remove the limit from the definition of the partial derivative with respect to x, the difference quotient remains f of x plus h comma y minus f of x comma y over h. This resembles a difference quotient for the derivative of a function of one variable, except for the presence of the y variable. The image illustrates a surface described by an arbitrary function c equals f of x comma y. So just as before, we're taking a point and we're trying to create a tangent line. In the image, the value of h is positive. We graph f of x comma y and f of x plus h comma y for an arbitrary point xy. Then the slope of the secant line passing through these 2 points is given by f of x plus h comma y minus f of xy over h. This line is parallel to the x-axis. Therefore, the slope of the secant line represents the average rate of change of a function f as we travel parallel the x-axis. As h approaches 0, the slope of the secant line approaches the slope of the tangent line. If we choose to change y instead of x, the same incremental value of h, then the secant line is parallel to the y-axis, and so is the tangent line. Therefore, df dx represents the slope of the line tangent line passing through the points x comma y, f of xy parallel to the x-axis. And df dy represents the slope of the tangent line passing through the point x comma y comma f of x comma y parallel to the y-axis. Next example. Use the contour map to estimate dg dx at point square root of 5 comma 0 of the function g of x comma y equals the square root of 9 minus x squared minus y squared. Okay, so recall contour maps from our past section, and it kind of tells us, we've seen this graph before, so it's a circle, and we kind of go ahead and write the contours of it, right? So these are circles within our figures, I guess you can say. So to estimate the value at point square root of 5 comma 0, we're going to take the derivative of our function in terms of x, and then evaluate at that point square root of 5 comma 0. So we first have to find dg dx. And we're using g instead of f just because this function is named g, not f. Okay, so let's begin by finding the derivative in terms of x of our function. The square root of 9 minus x squared minus y squared. Okay, so let's go ahead and take the derivative. So we have to work with chain rule. We take the derivative of the exponent of the outside, and the derivative of our inside. So that would just be, we're working with x only. So 9 is 0. The derivative of negative x squared is negative 2x. The derivative of y squared, well, y squared is just a constant, so it's 0. So that we have, well, our 2 and that denominator 2 cancel out. So we're left with x times 9 minus x squared minus y squared, negative 1/2. Let's make that negative 1/2 a denominator. So we're left with 9 minus x squared minus y squared raised to the 1/2 power. Now it's not negative, and x stays in the numerator. All right, so next we evaluate for our point. And y equals 0. So let's go ahead and find that out. So dg dx of x comma y equal to the square root of 5 comma 0, well, that gives us, we just substitute those values in. So x is square root of 5, and I forgot that negative above, huh? So this is a negative here. Negative the square root of 5 for x. In our denominator, we have 9 minus square root of 5 squared minus 0 squared. Okay, gives us negative square root of 5 over 4 square root of 4, which gives us square root of 5, negative square root of 5 over 2. If we punch this into our calculator, it's about negative 1.118. So what did we just find? We found the slope of the tangent line parallel to the axis in correspondence to the point, negative square root of 5 and 0. And why x-axis? Because we took the derivative in terms of x. Functions of more than two variables. So this is just expanding our derivative definition to another variable, z. Suppose we have a function of three variables, such as w equals f of x comma y comma z. We can calculate partial derivatives of w with respect to any independent variables. Definition. Let f of x comma y comma z be a function of three variables. Then the partial derivative of f with respect to x is written as the f dx, or f sub x, is defined as, so we already defined x, we already defined y, our new one is z. The partial derivative of f with respect to z, written as df dz, is defined to be df dz is equal to limit as m equals 0 of f of x comma y comma z plus m minus f of x comma y comma z divided by m. And notice we didn't use h. For each variable, we can change our arguments. Instead of h, we can make it any letter. Example, use the limit definition of partial derivatives to calculate df dx, and then find df dy, df dz by setting the other two variables constant and differentiating accordingly. Okay, so we're just left to find the partial derivatives of this function. Let's begin with x. So we're going to apply the partial derivative of our function x squared minus 3xy plus 2y squared minus 4xz plus 5yz squared minus 12x plus 4y minus 3z. Okay, let's go ahead and take the derivative of terms of x. Our x's, well, even though we have a very lengthy function, we only have 4 derivatives to apply. The rest are constants. So our answer is, well, the derivative of x squared is 2x. The derivative of x is 1, so we're left with minus 3y. Y squared, 2y squared, that's 0. The derivative of x is 1, so we're left with minus 4z. No x's, so that 5yz squared is 0. The derivative of negative 12x is negative 12. 4y would be 0, and 3z would be 0. So the answer would be 2x minus 3y minus 4z minus 12. We have found the partial derivative with respect to x of our function f of x comma y. Let's go ahead and find the partial derivative of y, of our function f in terms of y. So df dy. Our function is x squared minus 3xy plus 2y squared minus 4xz plus 5yz squared minus 12x plus 4y minus 3z. Okay, so let's go ahead and take the derivative. Now our derivative is for y, so let's notice where we have our y's. Let's take a moment to acknowledge our y's. Every term where a y is not included would probably end up being 0. Let's go ahead and work this out. The derivative of x squared, well, there's no y, so that would be a constant. That's 0. Negative 3xy, the derivative of y is 1, so we're left with minus 3x. 2y squared, that would give us 4y. Minus 4xz, there is no y, so that's a constant. 5yz squared, the derivative of y is 1, so plus 5z squared. Minus 12x, no y, thus the derivative is 0, plus 4y, plus 4. Minus 3z, no y, so it's 0. So our answer is negative 3x plus 4y plus 5z squared plus 4. That is our partial derivative with respect to y. I know it's a mouthful, so if you say df dy, though it's not mathematically correct to say, I know what you mean, and that is okay. Okay, so next we have df dz, the partial derivative of your function f with respect to z. So we want to find the derivative of our variable z of our function. So our function is x squared minus 3xy plus 2y squared minus 4xz plus 5z squared minus 12x plus 4y minus 3z. Okay, so let's highlight our z's. We only have a z here, here, and here. Everything else is a term without a z and would be considered a constant. So the derivative of x squared is 0. The derivative of negative 3xy, no z, thus 0, plus 2y, 0, minus 4xz, derivative of z is 1, so we have minus 4x, minus 5z squared plus 10z, minus 12x, minus 0, plus 4y, plus 0, minus 3z, negative 3. So our answer is negative 4x plus 10z minus 3. Not so bad, right? It just takes a little bit of practice. I know the notation looks a lot more intimidating than what it is, but once you recall our calculus 1, it's not so bad. Higher order partial derivatives. Just as derivatives of single variable functions, we can calculate these second order derivatives, third order derivatives, and so on. They're referred to as higher order derivatives, and we have them written right here. An alternative notation for each is f of xx, f of xy, f of xy, and f of yy. Next example, calculate the four second order derivatives for our function f of x comma y of x times e raised to negative 3y power plus sine of 2x minus 5y. Okay, let's go ahead and work this out. So when it's talking about the four second order derivatives, what is it asking? Well, we need to find the first order derivatives, right? So it's not asking for them, but we need to find df dx and also df dy. So what are the second order derivatives of which it wants? The four second order derivatives of our function would be d squared f of dx squared. We can also find d squared f of dy squared. And our partial order derivatives also include those of y and x in correspondence to the derivative of the opposite, meaning d squared f of dx dy and d squared f of dy dx. So above, we actually have the four ordered derivatives it wants. The four second order derivatives it's asking for. We have our first, our second, our third, and the fourth one that it wants. All those four. Okay, but before we get to any of those, we first have to calculate the derivatives of your function in respect to x and y. Okay, so the derivative of your function in terms of x. All right, so we have our function here. We want to find derivative of x. We have an x here and here, and that's it. So our derivative would be the derivative of x. Let me write it down. All right, the derivative of x is 1. The derivative of this x right here is 2. So our answer would be e raised to negative 3y plus that second term is not so easy because it's enclosed in that trig function. We have to do that chain rule. The derivative of sine is cosine. So cosine of 2x minus 5y. The derivative of 2x is just 2. Okay, so that is our function, our first function, df dx. Okay, now we want to find the second order derivative. Let's get one of them out of the way. No, let's go ahead and find df squared of f dx squared. So the second derivative in terms of x, of your function in terms of x. Okay, well, just so that we practice notation, this would be df dx of df dx. Okay, so we want the derivative of your function f from your derivative of your function f. So we have d dx of e negative raised to negative 3y plus 2 cosine of 2x minus 5y. Okay, so I need to find the derivative in terms of x. We only have one x there. So we were left with that first term would be 0 plus the derivative of cosine is sine. We would have negative sine of 2x minus 5y. And the derivative of 2x is just 2, so we would have a 4 in the front. So we would have negative 4 sine of 2x minus 5y. Okay, we got one down. Okay, we have the derivative of x, so let's find that second order derivative of your function x in terms of y. So next we want d squared f of dx dy. dy dx. Okay, so if we're using our function notation, which we have right above, or if you're using our definition, we're going to find this one. So this is asking for the derivative of y of your function of your derivative in terms of x. Well, we have our derivative in terms of x right here. So we're taking the derivative of your x derivative, but now you're applying the derivative of y. So you want d dy of e raised to negative 3y plus 2 cosine of 2x minus 5y. So yes, this is derivative of your function in terms of x, the first derivative in terms of x. But now we want to take that derivative and apply the derivative of y. Okay, where is our y's? We have our y here and our y there. So our derivative would be, the derivative of the exponent is just negative 3. And then here we have a cosine with the argument of y. The derivative of cosine is negative sine. So I have negative sine. And we have 2x minus 5y. The derivative of your argument, the derivative of 2x is 0. The derivative of negative 5y is just negative 5. So times negative 5. So our derivative is negative 3e to negative 3y plus 10 sine of 2x minus 5y. Okay, we're almost done. We found one of our other partial derivatives. We found df squared of dy dx. Okay, now you have two more to do. You want to take the derivative of y, and then you want to apply that second derivative. And then once you do that, you want to take the derivative of your derivative of y in terms of x. Notice, I think this is a helpful thing to point out, that one that's listed second, that's the one you are starting off with, that you're applying the derivative from. So notice that we took the derivative of our function in terms of x, and now we're writing it and finding the derivative in terms of y. So that's where we're pointing out those y's, because now we don't want the derivative of x. Now we want the derivative of y. Moving forward, Theorem 4.5, equality of mixed partial derivatives, Clairaut's theorem. Suppose that f of x comma y is defined on an open disk D that contains the point A comma B. If functions f of xy and f of yx are continuous on D, then f of xy equals f of yx. Let's see this in an example. Verify that u of xyt equals 5 sine of 3 pi x times sine of pi y times cosine of 10 pi t is a solution for the wave equation utt is equal to 4uxx plus 4yy. Okay, so what it's asking is we want to prove this, right? So we first need to find, that utt, which we know it's a derivative of your function dt in terms of your function dt. So you're applying the derivative twice in terms of t. And you need to also find the derivative of x twice. So we want to find the derivative of dx. And also derivative of y twice. We have to find each one of these separately from your given function. From your function that's given. Okay, so let's go ahead and apply those. Let's start off by finding, well, whichever one catches your eye first. I think I started with x. So let's find the derivative of x twice. So let's take the derivative. In our function x at u of xyt, we only have an x here. Everything else is a constant, but it's being multiplied, so it's not like it's being added, which is different. So the derivative of this would just be, well, the derivative sign is cosine, so it'd be cosine of 3 pi x. The derivative argument is just 3 pi. And then we keep everything else, we just bring it down. So our first derivative would be 15 pi times cosine of 3 pi x times sine of 4 pi y times cosine of 10 pi t. Okay, now let's apply a derivative of that first derivative. So that we get, well, we want the derivative of x. We only have an x here. So we only need to apply a derivative of this. The derivative of cosine is negative sine of 3 pi x. The derivative of your argument is 3 pi. So our answer would be 15 times 3 would be 45. Pi times pi is pi squared. So we took care of this, multiply it by that. And then we have negative sine, so I'll write the negative in the front. Sine of 3 pi x times sine of 4 pi y times cosine of 10 pi t. Okay, so just to start off again, that was our first derivative, and then we went ahead and found the second derivative in terms of x. Let's go ahead and do the same thing for y. So for the sake of saving some space, let's first take the derivative in terms of y. So if you look at your function, let's take the derivative in terms of y. So we only have a y here. So I only need to take the derivative of that argument with y. The rest are constants that are multiplied in, so I can momentarily disregard them. The derivative of sine is cosine, so I have cosine of 4 pi y. The derivative of pi is 1, so we're left with 4 pi. Okay, and then we multiply everything back in, or just write it next to it. So our first derivative is 15 times 5 times 4 is 20, so I have 20 pi of sine 3 pi x times cosine of 4 pi y times cosine of 10 pi t. Okay, now we want to take the derivative in terms of y. Again, for our second derivative. Again, we only have y here. The derivative of cosine is negative sine. We keep our argument, and chain rule makes us take the derivative of our argument. So we have the derivative of y is just 1, so we have 4y. 4 pi. Okay, so our double derivative would be 20 times 4 times our negative gives us negative 80. Negative 80 pi times pi is pi squared of sine of 3 pi x times cosine of 4 pi y times cosine of 10 pi t. Okay, we found that second derivative. One more time, lastly, for t. Okay, to save time, let's first find the derivative of our function in terms of t. So let me erase some past work. Okay, so here we have our function. We only have a t once. So I only need to take the derivative of this for it to be the derivative of t, of your function in terms of t. The derivative of cosine is negative sine, and chain rule makes us take the derivative of the inside. The derivative of t is just 1, so we're left with 10 pi. And then we bring everything else down and multiply it in. So our first derivative is 5 sine of 3 pi t of 3 pi x, not t, times sine of 4 pi y times cosine of 10 pi t. Okay, that last part was wrong. So we had negative 10 pi sine of 10 pi t. There we go. I was looking at the wrong part of my notes. Okay, let's clean it up a little so that we have negative 50 pi sine of 3 pi x sine of 4 pi y sine of 10 pi t. Okay, now let's go ahead and take the derivative in terms of t for our second derivative. So that we have our t is only here. The derivative of sine is cosine. So I have cosine of 10 pi t times derivative of t is 1, 10 pi. So 10 times negative 50 is negative 500. negative 500 and pi times pi is pi squared of sine 3 pi x times sine of 4 pi y times cosine of 10 pi t. Okay, so we did all this preliminary work and we just wanted that second derivative. So let's take a moment to highlight what we wanted. We wanted the second derivative, so we have that first one for y. We have that second one for x. And then we found that third one for t. And we're trying to prove that this equation holds true. Okay, let's see if it does. Let's go ahead and place that double derivative for x and double derivative for y. So we have 4 times negative 45 pi squared sine of 3 pi x times sine of 4 pi y cosine of 10 pi t. That's the first one, x. And then we're adding our double derivative for y. So plus negative 80 pi squared of sine of 3 pi x sine of 4 pi y cosine of 10 pi t. Okay, we want to show that the same as our double derivative in terms of t. So actually, we see we can add them because they're like terms. So if we add them, we get negative 125 pi squared of sine 3 pi x sine 4 pi y and cosine 10 pi t. And if we multiply it by 4, we get negative 500 pi squared sine of 3 pi x sine of 4 pi y cosine of 10 pi t. And is it the same as our double derivative for t? It is. Very cool. So we have proved that that equation holds true. That's section 4.3, partial derivatives. Thank you.